Next talk is going to be by Professor Scott Moura from UC Berkeley.
Hello, everyone. It's great to be with you in this really exciting workshop. I'm certainly learning a lot, and it's an honor for me personally to be amongst these excellent researchers, learn from them, and discuss. Today, what I'm going to talk to you flows nicely from Nali's presentation on demand response. We're going to talk about learning and optimization of distributed energy resources. And I'll talk about two projects, one that involves something called Hopfield methods, which I'll introduce and explain. And the other one is called SlrpEV. Both of these involve electric vehicles as distributed energy resources. And you will see the way in which AI and machine learning plays a role. Now, as I progress through, if you have a question, drop in the chat. I much prefer you ask me in the middle than at the end. And Alejandro, if I could ask, if there's a good one, feel welcome to stop me, and then we can have a short discussion. So let me proceed forward. So first, just an introduction to my group called the Energy Controls and Applications Lab. We focus on dynamic systems and control and optimization, and more broadly, data science, of which I see those two previous disciplines kind of falling underneath. And then from an applications point of view, we have a telescoping set that starts at the smallest scale with batteries and battery management systems, goes up a level to automated, connected, and electrified vehicles. And then at the highest level, we work at grid and infrastructure scale. And I'll really focus on those on that last category today. Let me also introduce my group. It is somewhere between 25 and 30 people. And one thing I'm quite proud of is, but we still need to work harder on, is making it a diverse and inclusive group. And I want to highlight that you're going to see some work by Bertrand Travacco, who's graduating right now, Mathilde Badawal, who will graduate within the next year or so, Hassan Obiad. We also have Teng Zhang. And you'll also see some work from undergraduates and master's students, Akshat, Deep, and Erman. Okay, so Nali talked about the duck curve, and many of you have seen it before, so I won't dwell on it, but I do want to tell you maybe a little bit of the history of the duck curve that you might find interesting. And it's relevant, not just because everyone talks about it, but because it illustrates the challenges of integrating clean energy technologies. So again, to review, on the horizontal axis, you have 24 hours in the day. And on this vertical axis, you have megawatts. And this is actually the net electricity demand for the state of California. So that is total electricity demand minus renewables. And so this picture that you're looking at right here was developed in 2012, almost a decade ago, right? And the context in which this analysis was done was when the state of California was analyzing, is it sensible to have a policy of 33% renewables by the year 2020? What's going to be the impact on the grid, right? Now, today, we now have a policy of 100% clean energy by 2045. But anyways, rewind about 10 years, they're doing this analysis, right? And they're looking at how the shape of this curve changes once you start integrating more solar, which is really the belly of this duck, if you will, that's getting fatter and fatter. And so the key point of the duck curve is this ramping from the late afternoon to the early evening, where this annoying thing happens called Earth rotating around sun, and the sun sets, everybody comes home, turns on their appliances. And what we need actually is to have some fleet of generators that are dispatchable and can ramp and follow that trajectory quite quickly. Traditional generators like coal, nuclear, even oil cannot ramp that quickly, right? So something needs to be done to integrate these renewables. Now, this was, if you will, a cartoon and a forecast of what we think the year 2020 would look like in the year 2012. So perhaps you haven't seen this. Has it actually looked like that? Do we see 13,000 megawatts ramp in 3 hours in the year 2020 or today in the year 2021? So here, I actually pulled some data just from last week. I didn't even have to search many days in the past to find something that was similar. This is actual data from the state of California, the California Independent System Operator, where you can see indeed there was precisely a 13,000 megawatt ramp during this 3-hour period. So actually, I think it's quite remarkable that a forecast 10 years ago held true, considering not just technology, but policy and behavior and so forth. Now, how is that happening? It turns out that the shale gas revolution happened during that period. So that's playing a role. But what you can see here is actually the sun is setting, so solar PV is going down. And large hydro is playing some role to supply that ramp. And indeed, natural gas is also playing some role. But actually, in the state of California, it is largely being supported by imports. So we are relying on the remaining Western US states to ramp up and down whatever generators they have. And those generators are not necessarily clean net zero emissions generators. They are made up of natural gas and other fossil fuel plants, right? So we're just kind of shifting the burden outside the states. All right, so within that context, I now want to talk about emissions. So you have the actual data from the state of California on the left, and then on the right is the marginal CO2 equivalent emissions from these generators. And the key point I want to make is that if you want to make a choice of when you're going to consume electricity in the state of California, do not do it in the evening. That is the worst possible time, in part because of this ramping problem, and we lose our solar PV clean energy. Now, meanwhile, a whole other revolution is happening in which we're trying to decarbonize not just electricity, but transportation. So we're going to take our entire transportation fleet and try to move it and dump it on top of our electricity system, which, at least uncontrolled, means that when you come home at night, there's this other appliance that you're plugging in your car, which is now going to take this ramp in the early evening and exacerbate it significantly. Okay. And so that's a big problem now because uncontrolled folks are going to return home and charge their EVs when CO2 equivalent emissions are typically their highest. Now, this is California specific, of course, but the thoughts can extend. So the opportunity here is obviously to control EV charging at some aggregate level, but now we're getting into consumer behavior. And what I want to illustrate in this slide is we want to avoid charging during this peak emissions period. And we want to do so at the fleet level. And I have a highlight of Caroline LaFloix's work. She's now at Tesla, working on optimization of energy resources. But it means a significant behavior shift as follows. So what I'm saying is we need to not flatten the duck curve, which there's way too many papers in the literature about flattening the duck curve. Really, the goal to mitigate climate change effects is to minimize emissions, right? Is to shift to minimize emissions, which is correlated with flattening the duck curve, yes, but that is really the end goal. But here's what it practically means in terms of how you charge your car. What I'm saying is you should do this. You should leave home with 30% charge. Go to work or whatever you do during the day with your vehicle and plug and charge in the middle of the day, like at work, in public workplace charging situations where you can align that load with clean energy generation. And then arrive home with 90% SOC and maybe don't even charge at home. This is kind of an inversion of a typical charging behavior, right? The human element here. Okay, now I want to get even deeper and talk about something that we need to talk more about in this community. And that is issues of inequity and justice when it comes to this energy transition, because we have a clear opportunity to address some of these injustices if we do this right, or exacerbate it if we do it wrong. So here are the facts. And this is work by my colleague Josh Hapty with his collaborators. Pollution inequity is a big issue in the United States. In fact, non-Hispanic whites experience almost 20% less PM 2.5 air pollution exposure than they cause. Blacks and Hispanics experience 50 to 60% more exposure than they cause, largely because these communities live in industrial areas or along transportation corridors or in agricultural centers which disproportionately expose them to these types of emissions. This is the place from a health impacts point of view that we need to think about decarbonizing. That's how we can kill two birds with one stone, so to speak, and address clean energy and pollution inequity. Now, I also want to say something to kind of awaken people when it comes to transportation electrification. This is data from 2017. I don't have more recent data, but I think the trends probably hold true today. And the message is so clear in this slide that I still like to show it. On the left, you have the distribution of income for all households in the US, right? So you can see relatively uniformly distributed according to those brackets of income. On the right is the distribution when you only look at the subset of households that own a plug-in electric vehicle. Now, what you clearly see is the people that own plug-in electric vehicles are people who are high income, highly educated, generally white. And this actually is generally not the population that benefits most from reducing emissions when it comes to health impacts. And part of the reason for this is what's happening here on the next slide. So on the next slide, this is a study by the International Council on Clean Transportation, which looks at the number of public and workplace chargers in 2017 and what we need to reach projected demand by 2025. And the point I want to make on this slide is actually largely charging infrastructure is deployed at home today, where we have single family homes, off-street parking, this pretty picture of the nuclear family, from the 50s or 60s. But a lot of people in the United States live in apartments, in housing in which they're renting, or they don't have off-street parking. And so public and workplace charging is a huge gap in terms of our clean energy infrastructure in which AI can help, right? But it's unleveraged, and it's going to hit us real hard in these coming years, especially as OEMs deploy their plans to electrify their fleets. Huge issue, and I'm going to try to address some of it in this talk today. Okay, so that's a long intro to then get into some more machine learning and AI ideas that help address some of these issues, Hopfield methods, and then SlrpEV. So I'll talk about Hopfield methods first. So let me tell you a reality of EV charging optimization that is not nearly recognized enough in the published literature. There is tons of literature. I probably get a review request every single day that optimizes aggregations of EV charging, and they treat it as this continuous optimization. Like you can control the rate at which an EV charges amongst a continuous set. And that's what I'm trying to illustrate here at the bottom. Continuous from 0 to 32 amps, for example. Actually, the reality is not like this. And I know it because we've built these charging stations in SlrpEV, which I'll talk about later, in which it's actually discrete. There's only integer values of amps that you can apply. It's integer from 0 to 32. Interestingly, you can't do 1, 2, 3, 4, 5 amps because the power electronics doesn't work properly at those low rates. So it's actually more complicated. It's an integer problem. It's not this beautiful textbook continuous optimization problem. So that really got us thinking, broadly about these types of optimization problems. So consider for a moment this mixed integer nonlinear program. So mixed integer meaning I've got these optimization variables X, and let's say the first P of them are binary, and the remaining of them are continuous from 0 to 1. And without loss of generality, I can say they're binary because I can do like a hot 1 encoding, and then the continuous ones, we can scale it from 0 to 1. Okay, so now we're interested in solving these types of problems, and specifically at large scale. Think thousands, tens of thousands, hundreds of thousands of these EVs, like at a California scale, for example. Now, you may be listening to this, and if you're familiar with the Millennium Prize problems in mathematics, this is related to the P versus NP problem. And I'm not saying that we've solved this problem. We have not. What I'm actually going to tell you the story of is a popular machine learning heuristic from the 80s and 90s that we've kind of maybe rediscovered, that was not properly understood. And I think we've given a deeper understanding of this, and it turns out to be powerful in some settings, limited in others, and I'll explain. And it's called Hopfield methods. Okay, now first, there are existing methods to solve these mixed integer nonlinear programs, and specifically mixed integer QPs, quadratic programs, particularly a class of methods called convex relaxation methods. And many of my colleagues here in Zoom, or those of you listening out in YouTube land, have been active in contributing to this area. And I've got a list of very popular methods, particularly in power systems, on the left. And I don't want to review them all, although pay respect to this excellent work. But I do want to highlight one method, binary relaxation, that is kind of intuitive and popular in its use, but limited. So let's do a little exercise and think about binary relaxation, a first option that you might come across. So the idea is like this. It's a stochastic approach to recover this integer constraint. So let's let XR, okay, be the solution to the binary relaxation. That is, forget binary x's. Let's just make it continuous from x, from 0 to 1. Then the resultant solution XR, we can use it to draw a feasible x drawn randomly from this distribution, which is 0, 1, which is a Bernoulli distribution parameterized by x sub r. And this solution, of course, can be suboptimal, but let's explore it for a sec and see how. So consider this optimization problem, a nice little textbook problem that you can use in a class as a nice example. The problem says, between 0 and 1, which one is closer to a quarter? So 0 is closer to 1/4 than 1. When we're limited to just 0 and 1. And so x star equals 0 is the optimal solution. Now, what does this look like if we apply the binary relaxation? We would, of course, get that XR is 1/4, right? And then suppose that we use that to randomly generate feasible solutions 0 and 1 by drawing from this Bernoulli distribution. And if you take the sample mean, it turns out what you're going to get ultimately, if you do this at large scale, like for an aggregation of these binary loads, is 3/16, which is worse by a factor of 3. So it gets you to kind of pause and think like, okay, which of these methods should we really think about? So I want to go into history to a method that I don't think is really well understood today, but was very popular in the 80s and 90s. And I kind of want to uncover it and try to re-explain it. So it comes back to Hopfield methods. Now, in 1982, John Hopfield used neural nets to model collaborative computation. So it wasn't learning, it was just forward simulation of these neural nets to do collaborative computations. And in 85, Hopfield and Tanks showed that these neural nets could be used actually to solve optimization problems. So a forward run of a neural net solves an MIQP, which is kind of interesting. And so the power systems optimization community in the 90s and the 2000s and in the late 80s actually started using this to solve like unit commitment style type of optimization problems and so forth. But it turns out when you look at that literature, power systems researchers admit that they didn't fully understand why it worked well. And they threw different sorts of heuristics on it, which I can explain if you ask me a question about it, to try to enhance it. But it turns out that actually doesn't work. We've proven recently. And then I think it lost popularity because it wasn't understood, kind of this misunderstood creature. So let me explain it to you. So here it is in one slide, and it's actually quite elegant and simple. So for a moment, let's forget about the constraints, except for these binary constraints and this these upper-lower bound constraints here. So this is the problem we're interested in solving with the Hopfield method. Now it goes like this. The Hopfield method follows the following nonlinear dynamics. It's actually a nonlinear dynamical system fundamentally, where what we have is the state variable, x sub h, right? And the rate at which it changes goes with the negative of the gradient of f with respect to x, not xh, x. Then xh, the state variable, flows through this nonlinear function sigma, and then the output is x, okay? And sigma is this activation function. So sigma is this activation function, as you've heard of in neural nets, and that's of interest, of course, because it seems like it's the kind of only flexible thing within these dynamics. Otherwise, it's quite simple, although we have this odd thing of xh being an internal state variable. It's the hidden variable. Okay, so that's all Hopfield methods is it's this funky nonlinear gradient flow. And so that's now what I want to highlight here. And I'm going to write a star on the slide. That means it's important. You can ignore everything else. Pay attention to this slide, because this is an important point. So Hopfield method turns out to be this nonlinear gradient flow. And I'm just rewriting the dynamics here. Now, I can manipulate this a bit, and under some assumptions about what sigma is, I can eliminate xh and rewrite this in just a clean gradient flow, where the important thing is what's in the brackets, right? This coefficient on the gradient of f, because that dictates how quickly, or if you will, the step size of this gradient flow. It's this composition of the derivative and inverse of sigma. So what in the world is that function, that object? So on the right, what I'm showing you is different activation functions on top. We've got different choices, exponential, tanh, sinus. And then on the bottom is this composition of sigma involving its derivative and its inverse. And this is key. This really gives you strong intuition on what's going on. So here's really where to pay attention. This object here is 0 at 0 and 1, right? So what it means is that once x approaches 0 and 1, it kind of arrests, it stops. Then in the middle, it moves quick. And all the different activation functions do is kind of characterize the rate at which you transition from moving quick in the middle to not moving at all at 0 and 1. And that's the intuitive concept behind what's going on with Hopfield methods. So once you see this, some of you may be asking, well, this just looks like gradient flow, but maybe not in some Cartesian metric space, maybe in some alternate metric space, with this Riemann gradient defined by this tensor, matrix tensor G. So then we started looking at a geometric interpretation of what's going on here. What is this metric tensor G? What is this alternate space in which we're doing gradient flow? And this gives kind of a nice geometric view on what's going on. So turns out that Hopfield is a natural gradient descent for f with these nice dynamics here, where this matrix tensor G just is defined by this composition of the sigma function here. So nothing really, really surprising. And then you can define like a differential length and an induced distance. And you got this cool kind of geometric interpretation for what Hopfield method is doing in this in this non-Cartesian space. So we can draw these concentric balls defined by this geodesic distance d sub g, defined according to this metric tensor, where what these contours show are they're equidistant in this transformed metric space, right? And you can see that it gets shorter and shorter as you get to 0 and 1. It starts moving slower and slower. So this is the geometric view on what Hopfield is doing. So here's a simple comparison to projected gradient descent, which would certainly be an alternative method. And what you see here is just a super simple example to two optimization rails, x1 and x2. And the optimal solution is going to be right here, this black star here, right? And we're going to run projected gradient descent in the Hopfield method. And of course, projected gradient descent just looks like, gradient descent on the unconstrained space, and then it projects back to the feasible set. So you can see that's what's in red on the right. And then Hopfield method, what it does is it moves slow when you're near 0 and 1, and in the middle, it moves quick. So if there was an audio version to explain this, it'd be like this. Projected gradient descent is like, boo. Hopfield method is like, it just kind of snaps, right quickly towards 0 and 1. But once you get near 0 and 1, important, it moves real slow. So you can get to near the binary solutions very fast, but then once you're near it, then it moves quite slow. That's the nature of this Hopfield method. So I'm not going to dwell too much on the kind of theoretical analysis, because if you're really interested, the papers are available to you to check out. But we've been able to prove nice properties like the iterates of Hopfield decrease monotonically the objective function given certain conditions. and then it converges within a set, and this is important. It converges into a set that contains the optimal solution for the original unrelaxed problem, but also other solutions, right? So you may converge the optimal solution or not, but the optimal solution is contained within the set that it converges to. And then we've also been able to show convergence rates, which is sublinear in comparison to a gradient descent, which will be guaranteed at a linear rate. Okay, so now some numerical experiments, just to give you a bit of a flavor. We've done other things that are applied to like unit commitment problems in power systems, but I think this kind of illustrates better what Hopfield methods do. So what we did here with Mathilde, whose picture will show up in a sec, is to basically randomly generate these MIQPs where the data here in the optimization problem is randomized. And then the competing methods would be with CPLEX, the MIQP solver. So this is using a state-of-the-art branch and cut method. Then relaxing the binary variables and just solving it as a QP and totally ignoring the binary constraints. You can also use a semi-definite relaxation, a little bit more sophisticated, and then this Hopfield method. And then we have different metrics that we computed, the objective functions, computation time, and the constraint violation, or CVs, if you will. So this first talks about computer running time. So although we've solved this for much larger problems, already you can see when you compare state-of-the-art branch and cut methods or semi-definite relaxation, which scales with like n to the 6, where n is the number of optimization variables, these Hopfield methods scale much better. So they really become appealing for these large-scale MIQPs. There's situations where it's not appealing, and happy to be honest about that. This shows actually the constraint violation and a comparison of the objective function value. Actually, the key point here, let me just get to the conclusion, is blue Hopfield method has nearly zero constraint violation. But as I said, it moves real slow once you get to near the binary solution, right? So after the fact, there might be some post-processing you could think about if you really want to enforce these binary constraints. Okay, so that's Hopfield. Now I want to talk about something totally different, SlrpEV. Now, SlrpEV stands for the Smart Learning Pilot for Electric Vehicle Charging Stations. And the goal here is to create the next generation of workplace and public EV charging that decreases emissions and helps break some of the economic problems with deploying workplace and public EV charging, which today almost uniformly is not economic. It's like free Wi-Fi, right? It's tries to draw people in maybe, or more relevantly, there was maybe some public incentive that they took an advantage of. But we need to make it economic to scale and also address some of those equity issues that I described before. Now, let me be clear here. This is not just some math and simulations. This is actual deployment of infrastructure, developing software to support it, dealing with partners at different sites. And I am literally day-to-day doing customer support for people using our charging station network. And I say that only because you start to realize what are real-world issues and what are gaps in the literature. So let me try to highlight some of the things that we learned, because I think it might be interesting. But the important scientific research objective is the following. There are a lot of pilots that try to optimize that optimize the charging schedule. What we're attempting to do is to simultaneously optimize the price along with the power by learning user preferences, which means really incorporating human behavior. So as I introduce SlrpEV, I'm going to introduce it as a cyber-physical and human system. So let's first talk about the physical part. It's a network of charging stations, 3 locations in San Diego, in an office building in San Jose in Silicon Valley, and then also at UC Berkeley. If you want to do something hard, deploy infrastructure at a public university. But anyways, so we have a total of 26 ports here, and actually our pricing optimization only happens at the UC campuses. All right, so that's the physical infrastructure. We also have a cyber infrastructure, a whole software platform we built on top of this. And let me explain it this way. is that when the user shows up, they scan a QR code on the station, and then they get this interface that you see here, and it generates a price that the user sees. You can see here, $2 per hour or $6 total cost for this flex option. The user makes their choice, which goes into the cloud, right? And that goes into the database. And then there's some optimization and learning that's happening, which is then optimizing the power schedule, which is transmitted to the EV charger. And then we have this so-called metrology data that's measuring the actual power and if they're connected and so forth. That's then being stored and continuously processed. Developed by Akshat and Deep. Actually, undergrads built code that is production level in this project. Now, here's the human parts. Star. That means important. Star. This is important. This is the key decision point where we're trying to incorporate human behavior by giving them a choice amongst a menu of two. Okay. And we have this ASAP option and flex option. So what does ASAP mean? ASAP is just the normal charging experience. It means that when you plug in, it's going to charge at max power until you unplug or top off. And the pricing for that is just a fixed rate, like in dollars per hour. Note, this is key. When they pick ASAP, it means charging power is uncontrollable. That is, they have not granted us the ability to manipulate the charging schedule. It is basically an uncontrollable load, right? Now, flex, and this is a version of demand response that Nali was talking about, kind of an alternate version here. Flex, here, the user will indicate their departure time with this slider, and then the added range of miles that they want from the charging session. And there we know the deadline and the energy amount that we need to deliver by that deadline. And then the cost is given as a total cost. And now charging power is controller, because within the constraints of delivering power by a certain deadline, we can design the power trajectory as we want, satisfying that constraint. So, but here's the most important thing to remember here. Basically, if I want to shift load, the question is, how much to discount flex relative to ASAP to acquire that flexibility? That's it. I want to discount flex by some amount, and I want to figure out human behavior, which can be diverse across these locations and amongst populations within the locations, to acquire some sort of flexibility and incentivize them to pick flex when it's advantageous to me to kind of shift the aggregate power. Now, to do this, we've actually engaged with something that is popular in machine learning, but has existed in behavioral economics for a couple decades. So using the so-called discrete choice model. So I'll give you just a quick intro to give you a flavor. This actually was created by Daniel McFadden, an economist that turns out at UC Berkeley, who won the Nobel Prize in Economic Sciences for this in the year 2000. And I'm not saying this is the best behavioral model, by the way. There are other models out there that use utility theory, but this one has a nice mathematical form that is nice for our algorithms. And it turns out it actually works super well for us. So, but anyways, the key idea here is the core of it is that for each alternative J, where J can be ASAP or flex, there's some kind of utility, let's call it U. And in typical econometrics style, it's this linear function of attributes, Z and W. And I'm going to make different Z and W and differentiate them by the fact that Z are attributes we control, think price. And then W are attributes I cannot control. So that's like, does the user have a charger at home? Do they have a salary that's more than $100,000 per year? If they do, then they might be a little more insensitive to the price differences, etc. Now, we don't here assume that people are robots. There's actually a perception error that's indicated by epsilon. So then U is actually a random variable. And it turns out that under a particular assumption about the distribution of epsilon here, you get this interesting mathematical form for the probability that they pick any given choice J, where J can be ASAP or flex. And it actually follows the softmax function, which is popular in machine learning, which mathematically looks like this. Now, we're going to come back to that in a sec. Now, first, some quick stats about SlrpEV. We've been running these experiments where we've been trying to learn user behavior by not optimizing, but actually randomizing the price And here are some stats over the past 6 or so months, which is honestly quite modest. But still, you can see we've delivered over almost 6 megawatt hours of energy, 20,000 e-miles, almost 350 charging sessions. You can see how it's distributed amongst the campus and the unique users we have. This is not impressive because of COVID, and we told everyone don't come to campus. So actually the next month is going to be very, very interesting as people start returning to campus, and usage is going to blow up, we anticipate, and there's going to be high demand for these charges, so charging stations. So it'll be really interesting what happens to this data over the next month or so. All right, so I'm not going to talk about learning the behavior model, but you can ask me a question. I'm going to talk about optimizing price and power. And actually, I want to back up and highlight the work of Songjay Bae, who graduated recently, now works at Honda Research Institute, and say that this system that I'm going to describe to you next is a particular case of what we call a human-actuated dynamical system. And it means the following. We've got this deterministic system. This could be our energy infrastructure, energy and mobility infrastructure, if you will. And we want to control it, but now we're not treating humans as some exogenous disturbance that we want to be robust to, but actually modeling them in the loop, right? In which their choices are like a stochastic input into the system. But very interestingly, we are going to consider the design of controllers in which, although their choices are random, they're conditioned upon this incentive control that we can design, in addition to, or in complement with, a direct control that might act on the deterministic system itself. So I'd now like to consider optimal control of these human-actuated dynamical systems. Now, I'm not going to go into all the nitty-gritty details of what it looks like for SlrpEV, but it turns out that the stylized version of what you get, and is actually running on the server supporting these stations, is this type of form where we're trying to minimize an expected cost. So we have the cost for each choice, H sub j for choice j, and it's the expectation. So it's weighted by these probabilities. And I want to highlight that Z, this incentive control, the price, the probability is conditioned on this price. So we can manipulate that probability, shift it a bit, right? Through this direct control, or sorry, this incentive control U. And then there's also controls here. Now, the question is, how do you solve these types of problems? And it turns out that H sub j is biconvex, and actually that I think is sort of generalizable. Actually, it's bilinear, and I'll tell you why in the next slide. What you get is this clean compact form if I write V and H in the following way. So this is now the type of optimization problem with some constraints that turn out to be linear that I would like to solve. So it's totally a nonlinear program. Everything here is admittedly continuous, in contrast to the thing that I emphasized earlier in my talk. Okay, so how to effectively and efficiently find solutions. Spoiler alert, we're going to formulate it into this multi-convex problem. So there's a lot of things going on here. Actually, I just want to highlight your attention on what the objective function looks like for each of these cases. Basically, what we have here is the cost is going to be something like the cost that we pay to the utility, C sub k, each time step, minus the revenue that we're going to generate and we optimize from providing charging service. So that's the price. That difference multiplied by the power. So we've got price times power. That's the bilinear or biconvex, if you want, form, right? And so that's what appears here and makes it non-convex in our optimization problem. And then we've got constraints that are unique to, can we control it because they pick flex, or can we not control it? There's just a deadline by which to deliver this energy that's on the right here. Okay, so a nice little math trick, just to highlight a bit, is you can do kind of a cute little thing in mathematically, which might even be an exercise in a convex optimization course. Actually, it literally was, and then we converted it into this work. Let me just give you a flavor. So let's denote LSC as this log sum x function, which we learn in convex optimization class is actually a convex function with respect to its argument. Let me define its convex or Fenchel conjugate as follows. And it turns out you can prove, and here's a little classroom exercise, that this inequality on the left is equivalent to V equals softmax function U. Why do we care? It turns out that this stylized optimization problem on the left, you can rewrite by replacing V equals softmax of this linear function in Z, which turns out to be the utility function in my discrete choice model, as follows. And then I'll expand the LSE function. And it turns out this is multi-convex in the optimization variables Z, U, and V, which means you can do a block coordinate descent. And this is very intuitive. It means freeze two of the variables and then optimize with respect to the third, rotate, and then do the same with the next variable, freezing the other two, and just keep going. So it doesn't converge provably to the optimal solution, but it's a nice, polynomial time way to get to a decent solution to these problems. Okay, so we've, these are simulation results. I think they illustrate better what happens. Here, we're just generating randomly choices that users make. They might pick flex, they might pick ASAP. And actually, I hid for you another detail, which is there's a third option that they're just upset with everything and they just leave and charge at home or charge somewhere else or don't charge. And what we've been able to show actually is you can reduce overstay, increase net profits, and increase the number of vehicles served significantly, making economically feasible these public charging stations, workplace charging stations, by optimizing price and power relative to no control. And this is the last slide. And I think this really illustrates what's going on here, which is quite simple, actually, conceptually. But the figure on the right is kind of a total absolute mess. It's very noisy, but there's actually a very clean interpretation here. So specifically, notice that the time of use price is what I'm highlighting in red here. And it's peak between 12 and whatever this is, 5 p.m. So basically, you don't want to use utility electricity between 12 and 5. So what's going on here in SlrpEV is during the peak price period and just before, okay, it's basically significantly discounting flex relative to ASAP. So you can see the flex in the dashed line all of a sudden become a lot less than ASAP in the solid line. It's really discounting it because that's the moment where it's really trying to incentivize people. Hey, pick flex, it's really discounted. We'll take the loss on the revenue because we can make it up by having less costs when we purchase electricity to the utility, all with a human in the loop here. Okay, so that's all. That's my talk. We talked about Hopfield methods to solve these MIQPs and the SlrpEV project. Thanks for listening. Looking forward to talking more in the panel.
Thank you so much, Scott. This was great. Let's see. So there's a question in the chat, a couple of questions. The first question is if the control could be optimized using DC fast chargers with a capacity greater than 50 kilowatts. Is that a possibility?
It's definitely, so I'm perceiving that this question is in reference to SlrpEV, and it's definitely a possibility. And it's actually easier because the problems I mentioned of only having these integer values at which you can control power go away. You can do it continuous with DC charging, and also with DC charging, there's a much wider range and it becomes more flexible. So that's a really great use case. I'll tell you, it's a little bit in contrast to the way they operate DC fast charging stations now, which is basically just move as many kWh as possible. So max power as early as possible, because the economics right now, how they're largely set up is, particularly with carbon markets like the LCFS credits, is just pump out as much kWh as possible. But once you get congestion, then you might want to do this pricing.
Right. Just out of curiosity, how many chargers do you have in the SLRP experiment?
So there's 16 in which we control price and power, but 26 in which we get data from. So there's 10 at this office park in San Jose that they want to provide charging for free for their customers. They said, we don't want you to charge them.
Okay.
So basically 16.
And it's all over the Bay Area, right? It's not just in the Berkeley campus.
No, it's just in the. God, I wish I could tell you how hard it was just to get it in the Berkeley campus. It's only one site in the Berkeley campus, underneath the gym, and then it's also at the top level of a parking garage on the San Diego campus.
I see. Okay. So it's in UC campuses. Okay.
Yeah.
Very good. I guess when was this installed? Because I was a few years ago at UC San Diego, and maybe it was one of those charges. I don't know. So anyway,
Maybe.
When did you install this in the first place?
It started 2 years ago. That's when we needed to really cite things and get approval. The Berkeley chargers went live last November, and then the San Diego chargers went live. They've been live for about 18 months, actually.
Yeah, no, definitely this was after I was there. Anyway, this was great, Scott. I really enjoyed the talk. Thanks, Scott. Thank you.